This is ECE 341 Random Processes. This will be part 1, lecture 5. To begin lecture today, we'll talk about the idea of independence. So events A and B are going to be considered independent if we can say that the probability of A given B is just equal to the probability of A, and conversely, that the probability of B given A is just equal to the probability of B. So if you think a minute about what this says, it says that if I know that B occurred, it doesn't in any way provide any additional information or any change in my understanding of A. So knowing B doesn't help me understand A in any different way, in any modified way. Same sort of thing with conditioning on A. If I know A, I won't know anything about B. I won't get any additional insight. I won't be able to modify or update or further refine my probabilities. So independent events are ones that knowing one or the other doesn't help you understand the other event. There's a consequence of this that I think is probably the more common way of showing independence. And in order to get that, I'm just going to remind us of what this idea of a conditional probability was. So when we first introduced conditional probabilities, we said that the probability of A given B, for example, was equal to probability of A times or intersect with B over the probability of B. So that was our definition of conditional probabilities. We know that if these guys are, if they are independent, so if A and B are independent, right? What do we know? I know that that probability AB can be represented as probability A, right? And it's still going to be equal to this probability of A intersect B over probability of B, which I can rewrite. Oops, I need to get that as a probability. So probability B, which I can rewrite by solving for that intersection probability, P of the intersection AB. So probability of A intersect B is just equal to the product of the probabilities, probability A times probability B, if those two events are independent. That's the only time that you're going to get that kind of probability coming out that way. So this is just an alternate way of looking at independent events. If A and B are independent, right? If they are independent, then we know that the intersection probability is just a product of their individual probabilities. So you can work with any one of these definitions. This helps us understand independence between two things. Independence is a larger concept. It can apply to groups of objects that are bigger than two. So let's go ahead and extend this idea of independence. It does get a little more thorny as we have a larger number of objects, but let's look at the following. So let's have multiple events, right? So we're going to go ahead and look at multiple events, A1 all the way out to some AN. These guys are independent. They are independent, if and only if a couple of conditions hold. The first condition is that each set that we can come up of n minus 1 sets taken from A1 all the way out to AN are independent. Each, maybe I should say that is, so each is independent. And I'll give an example of this here in a minute, independent. And that B, right, that the probability of the intersection among all n objects, so that's that intersection from 1 to n of my AIs, is equal to the product 1 to n of their individual probabilities. My guess is that most people would have guessed this second part, knowing what we had said about independence for pairwise objects, that the independent event A1 and A2, right, would mean that the intersection between A1 and A2 gives us the probability of A1 times the probability of A2. The one that might not have been quite so obvious is this idea that you have independence at that larger level also requires independence at the smaller level. And you can get condition B held without condition A being held. So it turns out independence for a large number of objects can sometimes be kind of painful. It can be a little bit tedious to try to show. Let me show this for the next largest size from 2. So let's go ahead and do a very quick example. Let's look at an example of 3 events, A1, A2, and A3. And I'd like to figure out what conditions would be necessary to show that they are independent. So 3 events, A1, A2, A3, are independent if, right, the following things happen. What was condition A? So A said that any set of n minus 1. So what was n? N was 3 in this case, so n minus 1. So any set of 2, right, are also independent. So that means A1 and A2 must be independent. And I'm writing this out just to be complete. So A1 and A2 have to be independent. A1 and A3 must be independent, and A2 and A3 must be independent. So how could we show that? We could show that by saying probability of A1, A2 was equal to probability of A1 times the probability of A2, that the probability of A1 and A3 was equal to the probability of A1 times the probability of A3, and that the probability of A2, A3 is equal to the probability of A2 times the probability of A3. Didn't do a terribly good job with that 3. Let's clean that up just a little bit. So we have this group of 3 things, right? And we have to look one dimension down. So now we're looking at pairs of them. And for 3 objects, the number of pair sets that we can get out of that is 3. We're going to look at that counting problem a little later today as well. So we're going to get good at counting the number of things that can happen. All of those pairs must display that independent behavior, that the intersection probabilities are equal to the product of the probabilities. We're not quite done because the B part, right? If you go back up here to B, it says that intersection 1 to n, and again in this case is 3. So the intersection of A1 up to A3 has to be a product of all their individual probabilities. So in this case for 3, this is also saying that the probability of A1 intersected A2 intersected A3 is equal to the probability of A1 times the probability of A2 times the probability of A3, right? So you can take a look at all of these different probabilities, and if each one of these expressions hold, then we would know that the sets A1, A2, A3 are fully independent across all combinations. A reminder again, it is possible to have sets A1, A2, A3 that their intersection probability is a product of their individual probabilities, but for which those pairs do not hold those necessary conditions, in which case the events A1, A2, A3 would not be independent. So you have to show it all the way down. Think about what this would mean for something like having n equaling 4. If I looked at n equaling 4, I'd have like A1, I'd have A2, I'd have A3, right? And I'd have A4. To show that those things are independent, I'd have to show that any group of 3 is independent, right? And then we'd have to show that the probability of A1 intersected with A2, intersected with A3, intersected with A4 was equal to the probability of A1 times probability of A2 going on out, in this case probability A3 and probability of A4. How many different groups of 3 are there? Well, there's going to be 4 such groups, And all of those groups require that stuff that we did before, which requires to show that any group of 3 is independent, you have to show any of their pairs are independent. So it just increases geometrically as the number of elements gets larger. It can be difficult to show that large groups are independent if you don't have further information or further justification where you know that independence is built in. So it can be difficult in these cases to try to show independence of a large number of items. Let's go ahead and move to another topic. If you're following along in chapter 1, this is also treated. It's under the idea of sequential experiments. So let's go ahead and think about this idea of a sequential experiment, sequential experiments. A sequential experiment is, I'm not doing a good job of spelling that out, experiments. Okay, so we're looking at sequential experiments. Sequential experiments are a lot like the terminology suggests. You have an experiment, right? Some sort of process that's going through and generating observations, but there's a sequence to it, right? You do one thing, and then that leads to you doing another thing, and that maybe leads to you doing a third thing, and so forth. So you can usually think of these guys as being a sequence of events. Oftentimes when we look at a particular problem or a particular process, there are natural sequences, and so they lead directly or naturally to this idea of a sequence experiment. For us, we're going to go ahead and try to use a graphical aid called a tree diagram to help us visualize these sequence experiments, at least if they're not too large. So one of the things we can do is we can visualize, and this is really for small sequences, generally small cases, right? If they get too large, this visualization gets unwieldy to be able to do. We can visualize these sequence experiments. We can visualize a sequence experiment using what is called a tree diagram. So let's go ahead and do this through an example. This sequence, by the way, because it is a sequence, something happens, and then based on that thing that happens, we do another thing. This naturally connects to what we had already seen as being conditional probabilities. So I'll make a comment to that just before we get in there, that the sequence of sub-experiments, naturally fits with our discussion of conditional probabilities. So let's go ahead and do an example of this. I'm going to go ahead and grab a little graphic over here just so we can get a visual on this. And so I'm going to grab a little picture here. Hopefully this will let me copy it over to my lecture. And so we'll go ahead and see. For whatever reason, it does not want to allow me to do that. There it comes. And so we're going to go ahead and bring that guy in. And I'm going to move it just a tiny bit. So let's go ahead and set that somewhere in here. And I think we're real close. So that will just save me from having to redraw that. It's not easy to draw socks. So let's do this as an example. Okay, let's consider a case where I've got a drawer of socks. So I've got a drawer of socks. And the socks that are in that drawer is right. I have one pair of red socks. I've got 10 pair of white socks. And just to be totally patriotic, I had 4 pair of blue socks. Okay. Being busy, doing the things that we all do. I didn't bother to match these up. I just threw them all loose into the drawer after I finished my laundry, for example. So you get up early in the morning and you need to put on a pair of socks. You don't want to bother everybody else that's in the room, so I don't turn on the light. I just open the drawer and I pull out 2 socks at random, put them on my feet, and I go to work. The question might be something like the following. What's the probability, right, that if I just grab those socks at random in a darkened room, grab 2 socks out of that drawer, where I've got 1 pair of red socks, 10 pair of white socks, 4 pair of blue socks that weren't matched together in the drawer, what's the probability that I'll end up at work with a matching pair of socks, right? So what's the probability? What's the probability? Probability if I select 2 at random, right? 2 at random, that I'll have matching socks on. So this fits nicely with this idea of a sub-experiment. We can visualize this as me going in and pulling out 1 sock, right? Pull out 1 sock at random, and then I go and I do the next sock after that. So let's go ahead and use this idea of a tree diagram and see if we can visualize this particular experiment. All tree diagrams start with some root. So I'm going to go ahead and just write a dot, and I'm going to say that that dot is the beginning of my experiment. That root, right, has some different possibilities that come out. And so I'm going to draw those different possibilities as branches on this tree, if you will. This is going to be a sideways growing tree, something like that. So we'll read this from left to right, right? And that each sub-experiment, right, is going to have its own series of branches that come up. What's my first sub-experiment? I select the first sock. So I'm going to put that above here. I'm going to go ahead and sit there and say that the outcome of this first sub-experiment is I'm going to pick the first sock, something along those lines. Now I gave 3 branches on this because all I'm really interested in this particular example is whether I have matching socks, and what's going to determine if they're matching or not is the color of the sock. So I have 3 different color socks, so there's going to be 3 different outcomes possible on me drawing that first sock, right? The first sock could be red, right? So the first one could be red, so I'm going to put a little 1 underneath that. First sock is red, or I could have the first sock as being white, or I could have the first sock as being blue, something along those lines. Each one of those has a particular probability, right? If I went back to the number of socks that were in here, I see that there's 1 pair of red, 10 pair of white, and 4 pair of blue. That's a total of 15 pair of socks. We know that each pair has 2 socks, so that whole thing gives me 30 total socks, something along those lines. So I know at least if I start out after a fresh laundry day, right, I've got a 30 total sock drawer, and I'm going to pick one of them. The chance of me getting that red sock on that first one, there's 2 red socks out of that 30, and so the probability of that, because they're all equally likely, they're just going to be different in color. So we're going to have 2 over 30, or we could call that 1 out of 15. I'm going to go ahead and write that probability right above the outcome in there. White is a little different, right? We've got 10 pairs in there. Each pair has 2, so that's going to be 20 total socks that are white that I could choose from out of the 30. That's going to be a 2/3 kind of possibility in there. So I'm going to go ahead and write in there 2/3. And then the last one, blue, right? We knew that there were 4 pair of blue socks. Each had 2, so that's going to be 8 out of the 30, or it's still going to be 4/15. So I'm going to get something like 4/15 on there. One of the things I'm going to notice on that is that when I have that first sub-experiment, right, I start and I draw something. I get whatever number of events that are possible out of that first sub-experiment, in this case 3. I can assign a probability. I could also assign count. If I didn't want to put 1 out of 15, I might say that there were 2 ways of getting red socks. So I could also do this as a count, right? I could say something like there were 2 outcomes associated with that. For the white, we knew that there were 20 outcomes associated with that. And for the blue, we knew there was something like 8 outcomes associated with that. So we could have also labeled this not with probability, but number of outcomes. So I'm going to throw that in there as well. One of the nice things about the probabilities, though, is think about what we get on a sum of all of those probabilities. If I take the 1/15 plus 2/3, what is 2/3? That's just 10/15. I'm going to put this in terms of a common denominator. And the last one was 4/15. If I do all of that, I get 15 over 15. That's 1. That's 100%. We need these branches to add up to 1, right? If you start somewhere, you gotta have a chance of going down one of those branches, and there has to be somewhere to go. That means all of their probabilities are going to have to add up to 1. So that's a quick check on these tree diagrams. Anytime you're running off from some node and look at all the branches on there, if you compute out the probabilities going on those branches, those probabilities need to sum to 1, something along those lines. Okay, so my experiment back here was pick the first sock. So I've got one of the socks that I'm going to put on my foot. I need the one that I put on the other foot. So I'm going to have in here a second experiment, if you will, that is going to be pick my second sock. So that's the second sub experiment. I do that after I pick the first one. And I know at this point that there's going to be three color choices for the second sock as well. So if I look at that red path, I could do something like this. I could have 1, 2, 3 outcomes possible on that. And what would come out on the second one? Well, the second sock could have been red, the second sock could have been white, or the second sock could have been blue. So I'm going to do those as a R2, W2, B2, something along those lines, right? In this particular case, then, I've concluded my experiment, and so I might think of the overall outcome in here. The first outcome is that I have a first red sock and a second red sock, or I had a first red sock and a second white sock, or I had a first red sock and a second blue sock. We can certainly see in that case, right, that there's the first case that is a matching case, right? So we have a first one that's matching, and those guys are not matching the last two in there. So only one of those paths ends up giving me that kind of matching group in there. I can also do some counting in here as well. I can count the number of outcomes that are possible for each one of these. If the first sock was red, right, I had 30 socks to begin with. I selected one sock. That leaves 29 left over. If I come and pick that second sock as red, only one of those 29, because there's only one pair of red socks, right? Only one of those 29 was red to pick from. So I know the number of outcomes there was 1, right? White following a red sock, well, there had been no white socks picked before. There were 10 pair. That means there would be 20 available in that. And blue would be the same thing because the red sock was first. We had 4 pair of blue. None of them had been picked yet. So there's going to be 8 outcomes going along on that side as well. So if I wanted to count this up, so I know what the outcome is. If I want to sit there and say the number of those outcomes that are possible, right? How many ways that I could have gotten that number of those outcomes, right? It's just going to be a product of the number of outcomes going along those paths, something along those lines. So in this first case, I know there are 2 ways to get that red sock first, and only 1 way to get the second red sock. So the number of outcomes there is going to be 2 times 1 is equal to 2. The ways that I can get that red and a white, right? Something along those lines. There's 2 ways to get the red, and there's 20 ways to get that white. So I'm going to get 2 times 20, and so all of 2 times 20 is going to be equal to 40 outcomes that are possible in that way. And the last one, red followed by a blue, is going to be 2 times 8, and that's going to give me a total of 16 outcomes. So now I should just be able to go through and finish this. I'm going to put the probabilities associated with the second sub-experiment in just a minute. We'll look at some of those in a minute. But let's just go ahead and finish out the rest of the tree here. I know that white as my first sock can have 3 paths off of there as well. So we see 3 coming off of that. And then the blue would have had 3 paths coming off there as well. And I think you can already get some sense of one of the limitations of these tree diagrams. If you have a lot of branches coming off of there, they can be a little bit difficult to draw out. That doesn't invalidate this as a technique that can help you visualize stuff. There's oftentimes that I'll have problems that involve some sort of sequence experiments that the numbers are very large. I would never want to draw the tree, but maybe I artificially reduce the dimensionality just so I can draw it out and get a sense of what it is that I'm looking for. It helps me visualize it, and then I scale that dimensionality back up to the final dimension that the problem was once I've gotten my head around what the problem is asking. So these can be really good to visualize, even if you don't use it for the size or number of elements that is your final application. So on the second one, if I do the white sock was my first draw, the second sock could have been a red, the second sock could have been a white, right? And the third or the second sock could have been a blue. So I could have gotten a red, white, or blue on there as well. If I wanted to go and think about then what the final outcome would have been in there, that would have been a white followed by a red. It would have been a white followed by a white, and it would have been a white followed by a blue. We can do the same sort of thing on the next one down. The blue could have been followed by a red, a white, or a blue. Okay, and then if we went and found those particular outcomes, that would have been a blue 1, red 2, a blue 1, white 2, and a blue 1, blue 2, something along those lines. Let's go ahead and count the number of outcomes on each of those. If the first sock drawn was white, right, we had one of those 20 picked out. The total number of socks to begin with was 30. You draw one, that's 29 left. How many red socks are left? If we didn't pick any of them, well, we still have 2 in there, so we're going to get a 2 in there. That white, we had already picked one white in this case, so that means there would have been 19 left in that case, and the blue would have had something like 8. If I wanted the number of equivalent outcomes here that are white on the first draw, red in the second draw, right? Because those socks are, even though they're the same color, there's different instances of those actual elements, like different individual white socks. If I took the number of outcomes in here, I'm going to get 20 times 2 on the first one, so 20 times 2, that's equal to 40. The next one is going to be something along the lines of 20 times 19, so I'm going to get a 20 times 19, that's equal to 380. And then the last one in here is a white 1 and a blue 2. That's going to be 20 times 8. So I'm going to get 20 times 8. That's 160, something along those lines. Going to finish this guy out. So blue was our third choice that we had on that first draw. Red, there were only 2 to pick from, so it would have been 2 on there. White, it would have been 20 since we hadn't picked a white sock on the first. Blue would have been something like 7 because one of our blue socks had been chosen on the first one. When I think of the total number of outcomes here, I would have 8 times 2, so 8 times 2 is equal to 16. Blue times, or the blue and white would have been 8 times 20, so I'm going to get an 8 times 20 on that. That's also 160 that we'd seen similar before. And then 8 times 7, right? 8 times 7 equals 56, something along those lines. If I continue again thinking about which ones of these give me matching socks versus non-matching, well, a white red isn't matching, a white blue isn't matching, a blue red, right, is not matching, a blue white is not matching, but the other 2 cases are a blue blue is matching and a white white is matching. So we're getting something closer to a full tree diagram now to help us visualize the sequence experiment. About the only thing I haven't done in this particular case is computed the probabilities of the final outcomes, right? Or the second level of this, that tree set of tree branches. And we're going to turn our attention to that here in just a minute. Let me go ahead and count, though, the total number of outcomes. If I add all of those numbers, let me actually return that back to blue just so we can keep that as being our kind of counts in here. If I add all of those numbers going on in there, I can sum all of those pieces up, and I'm going to get 870. So if you take 2 plus 40 plus 16 plus 40 plus 380 plus 160 plus 16 plus 160 plus 56, it adds up to 780. Here's another way you could get that. I can get that as being, you can check this on your calculator, it's 30 times 29. How do I get that? There were 30 ways that I could pick the first sock, and there were 29 ways I could pick the second sock. That gives me the total number of outcomes in this experiment. So I've got 870. Notice that even though I'm just doing this as a number of outcomes, because these socks, drawing a particular sock, would all be reasonably assumed to be equal likely and being able to draw them, we can get probabilities based on these number of occurrences, assuming that those likelihoods are equal, right? So I could look at something like this. I could look at the probability that I'm going to end up with matching socks. Matching socks, right? So probability that I get matching socks, I don't look like a fool when I go to work, is equal to what? Well, I'm going to come in here and take a look at the number of outcomes that are associated with getting matching socks. So I'm going to get 380, I have 56, and I have 2, something along those lines, right? So if I do that, I'm going to think about that. What's the probability of matching socks? I'm going to have something like 2 plus 380 plus 56 over, right? Out of how many? 870, something along those lines. So if I go ahead and I'm going to pull out my calculator, just make sure that we do this all appropriately in there. So I can go ahead in here and I can put in 2 and I can put 380 in there. And I'm going to, let me try this again. So do that again, and then 56 and add it in. We get 438. So this whole thing is equal to, so far, 438 over 870. And if I continue with that again, I can go ahead and compute that out as an actual fractional number, something along those lines. And so I'm going to get something like 0.5034. So just a little bit over, in this particular case, 50%, something just a little bit over 50% chance of me getting that match socks in there. Let's look at some other ways of getting these probabilities, some other ways of filling out these tables. We had already seen before, and maybe I can go ahead and just highlight these and I'll do it in a different color. So we had something like this, that 1/15th probability, right? We had something in here, that 2/3 probability. We had something in here, that 4/15ths probability, something along those lines. We could have done these not as number of outcomes. We could have done these as probabilities as well. What are the probabilities that would go on these next sets of branches? Just a note, right? These are all conditional. So if I looked at this first one, and it gets a little crowded, so I'm not going to do it for everyone, right? We would be looking in this first one here as being something like this. This is the probability that we get red on the second, given that there was red on the first, right? That is a conditional probability. And we already know what that is. There were 29 stocks to choose from, and only one left was red, so that's going to be a 1/29th. So I'm going to have in here a 1/29th for that first one. The next one down, right, we have 29 socks, of which 20 are white. So the probability of having that second white would have been 20 over 29. And the blue would have been 8 over 29, something along those lines. Take a look at these three probabilities, 1/29th, 20/29ths, and 8/29ths. If I add those all up, right, if I sum those all up, they equal 1. As we had noted before, all the probabilities that come on a particular branch set that have the same root have to add up to equal to 1. So all of these are the conditional probabilities. Everything is conditioned on having selected R1 first, right? And all of these probabilities that I would label on the second level of branches are all conditional probabilities. The experiment itself naturally lends itself to this idea of conditional probabilities. We had mentioned that before. I could continue doing that for the remaining pieces in here as well. And what do I get for the next set? I can see that the probability of getting red, if I had had the first one white, there were 2, and it's out of 29. So I'm going to get 2 out of 29 as a probability there. There's going to be 19 out of 29 for the next one, and there's going to be 8 out of 29 as the third one. Again, all of those guys add up to be equal to 1. So if I take those three numbers, add them up together, they do equal to 1, right? Third set is going to be the same sort of an idea. I'm going to get 2 out of 29 on the first, I'm going to get 20 out of 29 on the second, and I'm going to get 7 out of 29 on the third. And again, if you add those all up, right, add those things up, you do get equal to 1, as you would expect. All of the things that sum out of the same kind of root branch, right, have to have probabilities add up to 1. If you are going further along to the right, you're going deeper into the branch structure, the probabilities there are conditional probabilities. So we might just note that these are conditional, right? Conditional probabilities, and they're conditioned on the earlier branches, something along those lines. So let's think of another way that I might have gotten this probability of matching socks. If I look at instead these three outcomes that we're matching, right, in terms of probability, what do I get? I know that matching was something along the lines of red 1, red 2, white 1, white 2, and then blue 1, blue 2. What's the probability that I get a red 1, red 2? Well, it is going to be 1/15th of the probability of the first thing, right, times 1/29th of the second one. So I could go through and multiply those through. I would have 1 over 15 times 1 over 29. That is the probability that I'm going to get that red. You can go back and take a look at the definitions of our conditional probabilities. This is aligned with one of those theorems, and it's just a way of getting that red 1, red 2 probability. So we're just going to multiply the probabilities going down the branch to get that probability of that particular outcome. The white 1, white 2, right, is going to be what? That's going to be a 2/3 times 19/29. So we're going to have a 2/3 times 19/29. So this first one was red 1, red 2. This next one's white 1, white 2. And then the last one in there, the blue and blue, is 4/15 and 7/29. So 4/15 times 7 and 29, something along those lines. and that's my blue 1, blue 2. Each one of these guys is mutually exclusive from the other. So I can get the probability of any one of these, right? Red 1, red 2, or white 1, white 2, or blue 1, blue 2. That's that union. The union probability of disjoint events, right? And everything that comes out on one of these branches is going to be disjoint. This idea of the total probability here there is just going to be a sum of those pieces. If you sum those numbers up, I'm going to just carry it out on my calculator so that we can see this out. So I'm going to take the first number, that's 1 over 15, and I'm going to take 29, 1 over that guy, and I'm going to multiply them together. And this first one is like 0.0023. Very unlikely I'm going to get a pair of red matching socks on there. The next one, I'm going to have something like 2/3, right? So I'm going to have that guy, and then I'm going to take that one, 19/29, and I've got two numbers then, and I'm going to multiply those guys together, and that's something like 0.4368. So pretty high likelihood of the white white. The blue blue is going to be something like 4 times 7. That's going to be that 28. And then I am going to go ahead and divide by the 15, and I'm going to divide by the 29, and that gives me a 0.0644, something like that. Now, if I take that 0.0644 and I put in that 43.68% and add it in, and then I take that 0.0023 and add that in, I end up getting that whole thing summing up to being 0.5034, just like I had before when you take account of all the rounding that goes on there. So both of those guys equal one another as we would have expected. So what have we gotten out of all of this? We've just introduced this idea that there's something called a sequence experiment. A sequence experiment is a collection of sub-experiments, one that follow another, to help us visualize these experiments and the way they interact and the way we can compute probabilities. It's oftentimes advantageous to use something called a tree diagram. That tree diagram we illustrated with this sock example where we picked one sock and then followed that with picking a second sock. We can see that we start the experiment with our first sub-experiment. That gives us a set of outcomes. Each one of those outcomes has further outcomes, and those further outcomes are conditioned, right? So all of these fall along the lines of a conditional probability. We can do things like count the number of outcomes for each one of these branches, multiply them together, and take ratios of outcomes to find probabilities, or we could just actually label each one of these as probabilities as well. And you multiply the probabilities down the branches to find the overall probability of each outcome piece. And because they are naturally disjoint, whatever final event that involves whichever number of outcomes, you can simply get its probability by adding them up. So it turns out to be a pretty nice tool as long as your sample sizes themselves or your number of branches on these things is a reasonable number. There's two other things that I would like to do before we get to this topic of counting. Some of these are a little bit in the book and some of them are not. I just want to make sure we're dealing with, again, ways that we can represent particular situations or maybe even this idea of sub-experiments. So a little bit of visualization, I'm going to say some additional notation or visualization. We're going to look at two quickly, and then we'll open the idea to counting. So how about this first one? We are going to think about something that is called a Cartesian, Cartesian product. This Cartesian product between n sets, and you might have that A1, and it's just going to be shown as a cross, A2, crossed going all the way out to AN, something along those lines. What this does is it gives us what is called an n tuple. Okay, it's an n element ordered set, if you will. So it's an n tuple. It's an ordered set. Okay. And I think probably the best way to help kind of introduce this idea of a Cartesian project, it's something you've probably seen before. You might not have heard it taught this way. Is I'll give a couple quick examples. Some quick examples might be something like this. If I take the whole set of real numbers and I take the Cartesian product with another set of real numbers, right? That gives me what you might call the real squared, which is what? It's an ordered pair. X is the first real number, Y is the second real number, and you might think of that as it being the Cartesian plane, X and Y, right? For any value of X, there's a whole bunch of values of Y, right? They give us, in this particular case, this Cartesian product. It gives us for any value of X, all the possible values of Y. That's how we get this Cartesian plane. The Cartesian plane is the Cartesian product between two reals. So my guess is that you have seen Cartesian products before. There are some different ways of doing this, and I think this next example shows some of that flexibility and how it might be a little different than you've seen before. So let's look at this. Let's look at a set A as being equal to the values x, such that x is on the closed interval 0 to 1, something like that. And I'm going to let B be equal to a set, and it's just a set of numbers, integers. There's only three possibilities. It could be 0, 1, or I meant to write a 2 there, so let's go ahead and make that as a 2. So I've got two sets, A and B, and I would like to think of what is the Cartesian product between these. Remember, what that does is it gives us a pair, right? It's this ordered set, right? We're going to have a first element from A, we're going to have a second element from B, but there's a lot of different possibilities in there. I would like to get a visual in this case, and again, I think a graphic. This isn't a hugely complex one, will help me. So if I think about something along the lines of what came from set A and what came from set B on the horizontal and vertical axes, respectively. This Cartesian product just basically says the first set lives on the horizontal and the second set lives on the vertical. So what does X, or the set A, do? Set A goes from a value 0 to a value of 1, right? And so I think of it as going on that interval 0 to 1. For every value B, the set A can go from 0 to 1. B has only three values. It has 0, 1, or 2. So if I take B and I look at its value 0 here, and a value 1 here, and a value 2, now I think I've got enough information that I could go ahead and I could draw this overall Cartesian product. Let me do that like this. So we're looking at this Cartesian product between A and B. When B is equal to 0, X can be any value between 0 and 1. When B is equal to 1, X could be anything between 0 and 1. And when B is equal to 2, X is being anything from 0 to 1. So this red in this two-dimensional graph right now does show that Cartesian product between sets A and B. Notice that the first one we did, right, it covered this entire place, right? Because both X and Y covered all the real values. So this thing went across the entire two-dimensional Cartesian plane. Down here, we have more restricted sets, and those more restricted sets, right, the cross product for any value of that x1, right, we can get it for any one of the values of y. That cross product just gives me the intersection between those two. And so I get something in this case that looks like a ladder. So the Cartesian product provides us a nice way of looking at ordered sets, where those ordered sets come out as for any value of one also being associated with or connected to a value of another, something along those lines. A second one that we might try to do here is an idea of a coordinate system representations. This is something kind of similar, but I'll just say a coordinate. Let's look at a coordinate system representations. And by the way, if a lot of this seems like I'm trying to do a bunch of stuff that involves some graphs and getting graphs or pictures going, it absolutely is the case, because this graphical depiction really provides us a way of managing information and visualizing a problem. It can help us solve it even if the dimensionality of the problem is larger than what can easily be accommodated by that graph. So a coordinate system representation, I might just say, is a useful, it's a useful visualization. It's a useful visual for some types of combined, or you might even think of them as sequence experiments. And we don't have to get too formal on this. I think I'm just trying to get across this idea that there's a lot of tools available to us to try to help visualize things and their dependence. So let's try again to show this coordinate system representation through an example. So let's do a sequence experiment like the following. it's just basically saying we're going to use a coordinate system to help us visualize stuff. So I'm going to choose, let's say, choose my horizontal -1 less than x less than 1 randomly. So I'm going to choose x such that it just falls on an interval 0 to or -1 to 1, something along those lines. So that's kind of like my A experiment, and then I'm going to follow that. So that's the sequence to some B, and I'm going to choose another random variable, and it's going to go from 0 less than y less than or equal to the root of 1 minus x squared, and I'm going to do that guy randomly. We still haven't really fully gotten as to how we might think about that random choice, but I think it's okay for right now. We just know that we're going to cover from -1 to 1 on x, and that y, right, is going to go from 0 to the square root of 1 minus x squared. I'd like to get some sort of understanding of what kind of pairs of values x, y are possible. Notice something here, that we have an x chosen to begin with, and that comes into play in my sub-experiment, right? So I'm seeing in this case that I really can't think about what I'm going to choose y to be until I've gotten x. If I go ahead and draw this out in the coordinate plane, I think I get a lot of insight into this. So I'm going to go ahead and show this with something x, and I'm going to show something y. X goes from -1 to 1, right? So we know that happens. And then once we have that x chosen, y goes from 0, so I'm going to put that just a little heavier in here. Y goes from 0 to the square root of 1 minus x squared. Well, what does that describe? That describes basically a circle, right? And so we're just going to get this circular, well, half circle going over there, something along those lines. So this thing follows root 1 minus x squared. The equation of a circle is x squared plus y squared equals 1. If you solve for y, at least the positive side of that, you'll get positive root 1 minus x squared. So y can be between 0, right, and that upper bound, which is defined by a circle. So if I go ahead and just shade this whole thing in, this gives me an indication of the value pairs x, y that are possible through this combined or sequence experiment, right? We can certainly see that x can go between -1 and 1, right? And then the y's value varies depending on x. If the size or the magnitude of x is pretty small, that means there's a greater range that y can be. The closer that our choice of x gets to 1 or -1, the range of y diminishes, and it diminishes down to the point of 0. So if I actually chose a value of x equaling 1, y could only be equal to 0, right? That's not much of a choice at all. If I move just a tiny bit off of x, right, my possible values there of y are much restricted compared to the values of y that are possible in the case for x equaling 0. So this is just something that helps us understand this sequence experiment, and it helps me visualize the dependence of the variables x and y. Something that I would note in this particular case is that we have sort of an opportunity here to consider maybe an alternate way of viewing this same experiment. Once I see this, right, I see this guy, I can say here maybe, in this case I can, visualize, other sequences or other sequence experiments, right, to get the same kind of space or visualization, right? So let's think about this. If you look at this, we started out by picking x between -1 and 1, and then we chose y, right, based on something that was to do with x. It's also possible that I could pick y first, right? That's sort of changing the nature of the sequence. What are my values of y that are possible here? If I look across all things, y can go 0 to 1, something along those lines. So I could consider something like the following. I could sit there and say, choose, right, 0 less than equal to y less than or equal to 1. Right? Could do that first, and that could lead to a second sub-experiment that says what? I'm going to choose x, and how would I choose x? If I've got a value y, and I'm going to do this in red, I've got a value y, x is going to go from this edge over there to this edge over here, which is still defined by that basic equation of a circle. We know a circle is 1 equals square root, circle of radius 1, of x squared plus y squared, something like that. Solve this for x, and what do we get? We end up getting, in this particular case, x squared plus y squared equals 1, or I'm going to get in this particular case that x squared equals 1 minus y squared, or x equals plus minus square root of 1 minus y squared. This is the negative sign, this is the plus side. So I could come down here and say, let's choose that x such that minus root 1 minus y squared is less than equal to x is less than equal to root 1 minus y squared. It's a little different visual, right? And we're choosing both of those guys randomly. So we choose this guy randomly, right? And we choose this guy randomly as well. And what we find out of that is that we get this same, right, kind of visualization that we would have gotten there. We just did it as y first, and then we did the x. So we did, well, that's not turning out so great. So let's try this again. So this particular one still gives us that same piece here, right? But we did y first, right? We did y first. Wow, really do need to take an extra second first. And then we ended up doing x second. So we reversed kind of the sequence order here, but still got that same result. So I think these graphic representations, right, this coordinate system representations can help us visualize things like sequence experiments and the dependencies that might exist between elements in that sequence or sub-experiments in that sequence. Okay, so I had intended to start with some counting, but I think I'll save that for our next lecture. So next lecture, we're going to begin a process of figuring out how to count things. This sounds a little bit weird, but if we want to get probabilities, part of the fundamental way we might find probabilities is seeing how many things lead to a particular result out of how many things total. We already saw some of that back in our example that used this tree diagram. We counted number of outcomes, and in this particular case, I think the counts were easy to do. Sometimes they get much more difficult. If I can become an accurate counter, I'm going to probably have an advantage in trying to figure out likelihoods or probabilities. So next time, we're going to formalize some counting strategies, ways to count number of outcomes, and they can get very large, and they can get very large very quickly. So we'd like a systematic way of counting outcomes. That'll come next time.